Hello, everyone. Yeah. Uh, today we are going to start our joint class for today. But before that, we will take pictures together. So please open your camera. And once again, please change your name according to what has been sent it by Nabila in the chat room. Your student ID and then your name. And please open your camera. Nabila, please help taking picture.
Yes, Dr. Lucia. Everyone, please turn on the camera and we're going to take a picture. And please change the display name according to the format that I've sent before.
Okay, please open your camera, guys. Okay, should we start, Nabila?
Yes, I can start. So there's only one slide. 1, 2, 3. Let me It's done, Dr. Lucia.
Okay, thank you, Nabila.
Thank
Okay,
you.
before we continue, let us open this class with an opening prayer. Dr. Vera, can you help with the prayer?
Bismillahirrahmanirrahim. Allahumma sholli ala sayyidina Muhammad wa ala ali sayyidina Muhammad. Allahumma ighfir li dunubi wal walidayya warhamhuma kama rabbayani shaghira. Rabbi ishrah li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Rabbi zidni ilma warzuqni fahma.
Thank you, Dr. Vera. So our agenda today is we will make a quick review for Module A3. We have checked all Module A2 that you have been collected to UNER e-learning system. There are 20 submissions that have been made. And today we are going to continue with a quick review for Module A3. As we have reminded you last week, the level of difficulty in Module A3 is higher than Module A1 and A2. So if I were you, today, Dr. Vera will deliver the review for us. Since it is more difficult than the previous one, if I were you, I will pay close attention to what Dr. Vera will explain. Okay, so without further ado, Dr. Vera, are you ready?
Yes, I'm ready. Dr. Lucia.
Okay. Please, Dr. Vera.
Okay, I will share screen first. Thank you, Dr. Lucia. For you all, have you downloaded the module A3 and have read? Yes? Okay, good. So we will discuss it today. Okay, I will start to explain the module A3. Thank you. Okay, module A3 is about atomic ionization energy. And like the two previous module, we always, after the title, we will face the objective. But you will see that the objective is different with module A1 and module A2. What is the difference? In module A1 and A2, what is the objective? You have done the module A and module 2. Have you already forgot? Yeah. What is the objective in module 1 and module A2? First is identify the physical problem and also computational problem. And then the second objective is check the validity of the DFT calculation. So in the module A1 and module A2, you just learn how to identify two kinds of problems, physical problem and computational problem. And then the second one is check the validity. But in module A3, we assume that you already finished with module A1 and module A2. So you no longer have problem to identify which one is physical problem and which one is computational problem. And you can also validate your DFT calculation. So now we have the higher objective. The first one is design a plan for a simple calculation project. So now you will have a simple calculation project in A3. And your task will be design a plan. And then the second one is evaluate. Not check anymore. It's check is whether it's valid or not. But now we use evaluate here. So you judge or you check the quality. Here, you evaluate the accuracy of the FT calculation based on the atomic ionization energy. So we use the atomic ionization energy to evaluate the accuracy of the FT. How do we know the accuracy of the FT calculation? From the previous one, compare with the experimental result. So we need to find the experimental result in the atomic ionization energy. So that's why here, the additional, you will use the CRC Handbook of Chemistry and Physics to find the experimental values. Have you looked for this book? Search for this book? Yeah. Okay, good. So we have two objectives here, and we need to have this book to evaluate the accuracy of the FT calculation because we want to compare with the experimental result. Here, the introductions. Ionization energy is one of the 5 quantities of hydrogen atom accurately predicted by quantum mechanics. From the Dr. Fabian lecture, we know that if we understand hydrogen, we can understand all atoms in this universe. And quantum mechanics can predict 5 quantities of hydrogen atom accurately. The other four, so one is the ionization energy that we will run in module A3. The other four is ground state energy, the radius of hydrogen, the spectrum, and also the spin. In the case of hydrogen, the energy required to ionize hydrogen, we can see here, this is hydrogen atom. And then we take one electron. So we have hydrogen cation here. So how much the energy that we require to ionize hydrogen? How many electron hydrogen have? One. So if we want to take one hydrogen in hydrogen atom, how much is the energy? So the energy is exactly the same with energy of its ground state. Or first as hydrogen atomic orbital. From module A1, how much is the hydrogen energy of its ground state? Minus 30.6 electron volt. Good. So how much the energy to ionize hydrogen? If you see minus 30.6, it means the bonding energy. So when you say the required energy to ionize, so it will be positive. So 30.6 electron volt. The energy needed to take one electron. Or the first, you can check in module A2, because in the module A2, you tabulate the, what to call this, hydrogen atomic orbital, right? The energy of the atomic orbital. You can check there how much the energy. So there is two ways to calculate the ionized hydrogen. First is from the its ground state, and the second one is from the orbital energy. However, the case will be different for many electrons. So this one is only applied for hydrogens. There are two forms of ionization of atom, including hydrogens. Either they release electron, so they release electron, or and become positive ion, or we can say cation, or accept electron and become negative ions. So if you release electron, you will become positive. If you take or accept electron, you will be more negative. And we may write these two possibilities as follow. So there are two equations here. First is equation for release or take the electron. Here, accept electron or release electron. Accept electron. So the first one will be A is the symbol of atom. You can put any atom here. The symbol is A. And then we accept electron. So A will become negative ions. And the energy require this reaction happen, or energy, the ionization energy is electron affinity. Okay, this is for the accepting electron. And the second one is if the atom release the electron. A is the neutral atom, and then they release one electron, and it's become the positive atom, or positive ions here. And the energy, we call it ionization potential. So now you know the difference between electron affinity and ionization potential from the equations. So this is the two most important equation in module A3. And we can measure both quantities in the experiment. So we can measure the electron affinity and also ionization potential from the experiment. We even already have their values for most atoms. Therefore, we can use these two quantities to evaluate the accuracy of the FT calculation. So we can calculate these quantities with the FT calculation, and we also have these quantities in experiment. So we can compare to evaluate the accuracy of the FT calculation. Okay, from here, is there any question? Can you follow? Okay. Okay. Here, the prerequisite. First, you must complete module 2. And the second one is you can access to CRC Handbook of Chemistry and Physics. Okay, now we will go on in the project description. Okay, I will make it bigger. Dr. Lucia, can you hear my voice clearly?
Yes, Dr. Vera.
Yes, yes.
Okay, thank you. So this is the project descriptions. Your task is to calculate both ionization energy as described in reaction 1 and reaction 2. And for particularly ionization potential, you calculate two cases, the singly and doubly ionizations. So here, you will calculate electron affinity and ionization potential. So you will have neutral atom and you take one electron. That is the first calculation. But for ionization potential, you will have two cases, singly and doubly ionization. So you will take the first electron, and then the second one, you take two electrons. So there is three cases that you will calculate. For electron affinity, only one case. You just put one electron. You just add one electron in the atoms. But for ionization potential, you need to check on the singly and doubly ionizations. So there is three cases that you have to calculate. And your objects are hydrogen atom, one atom with the valence electron in the 2s orbital, and then one in 2p, one in 3s, one in 3d, and one in 4s. So total you will have 6 atoms. So everybody will calculate the hydrogens, and the other is up to you. As long as it has 2s orbital, 2p orbital, 3s orbital, 3d orbital, and 4s orbital. So you will have 6 atoms. So maybe the group 1 and group 2 maybe will have a different atom choices. So you have to choose 5 atoms and include 1 hydrogen atom. Okay, understood? Okay. And you will use B3LYP with 2 techniques of calculations, unrestricted and restricted, with only 2 variations of basis set, 631G and 631G DP. Okay, so I will give you maybe 1 minute to read the project descriptions. And if you have question, you can ask now. If no, I will continue with demonstrations. it clear enough for student from Unsur? No question from Unsur?
Student from Unsud? No question? There is no question, Dr. Vera.
How about UTM? Okay.
They say, okay, no problem.
Alhamdulillah. Okay. How about you guys? Oh, there's question from Dava. No? I think he's shy. Us. Okay, I will continue if there is no questions. So this is the result in this question. First, you need to read the reference one and explain what the electron affinity is. So the definition of the electron affinity and how to measure it experimentally. So what is the definition and how to measure it experimentally. And then you briefly explain as well how to read the table given by reference one. After that, we will check the reference ones. And then the second one, it's also the same with number one, but with ionization potential. So you give the definitions and then you explain how to measure it in experiment. And then the third one, how to read the table, the experimental table. And then the third, using the format of reaction 1 and 2. So you will have how many atoms? 6. 1 hydrogens and you will have 5 choice atoms. So you will have how many reactions? You will give this format. Here, using the format of reaction 1 and 2, write the ionization reaction from the 6 atom and explain briefly the reason you choose the 5 atoms other than hydrogen. So you are the one who choose. So you need to explain why the reason why you choose that. So if you have 6 atoms, you will have 12 reactions. Yeah, so you have 5 reactions. So just exchange the A with your atom. Can be hydrogens or helium or yeah, and so on. Understand? Okay. In the number 4, write your plan to finish this project and consider when to use the restricted and unrestricted spin method in your analysis. So you need to have plan. So how many calculations? How did you design your calculations? And after that, you will tabulate your result for both energies and their counterpart of the experimental values. So you will have table with the both energies and also experimental result. And after that, you have to discuss the effect of method and basis set on the accuracy. So you will have comparative analysis. And then the 7, draw the valence orbital of the atoms like you done before in the module A2. And then you check before and after ionization, what will happen in the energy level diagram. Is it stabilized or unstabilized? So using the question in question 7, discuss the stability of the orbital after the ionizations. And then the question 9, maybe we can you use questions 8 to estimate the electron affinity and ionization potential for singly and doubly? Yes, we can. The answer is yes, we can. Then estimate them and compare the result with the result from the equation from question 5. And in the conclusion, you will evaluate your plan and then evaluate the accuracy of the FT calculation on atomic ionization energy. Okay, I will explain you from result and discussion from 1 to 5, especially 5, how to tabulate the result. So I will give you demonstrations here. Here's for case study hydrogens. If we want to make the equation for hydrogen, sorry, I have to move this. So one atom will have two equations. First is equation to take electron, and the second one is to add electron. So this one is for the electron affinity, and the second one for ionization potential. For hydrogen ionizations, this is the hydrogen, and then you add one electron, it becomes cation, anions, cation, and then hydrogens, we release one electron and become hydrogen plus here. From the introduction, we know that the hydrogen ionization potential is exactly the same with the energy of ground state, the 13.6 electron volts, or 1s hydrogen atomic orbital. But we can also calculate. What we need to calculate? The hydrogen atom, the hydrogen minus atom, and also hydrogen plus atom. So we can calculate the energy of product and then extract with the hydrogens. Can you calculate the hydrogen atom? Hydrogen minus? And then H plus? Okay. Try to calculate H plus. Can you? Maybe just 1 minute to calculate H plus. Can you calculate H plus? No. What is the error? Okay, we will wait. We'll continue. So the question is, can you calculate hydrogen plus in the FT? Really? Can you? Hydrogen plus. Error. So why it is error? What energy did you calculate? The electronic energy, right? In the case of H plus, how many electrons there? There is no electron, so that's why you cannot calculate it in DFT. Yeah. So for H plus, you cannot directly calculate because it has no electron. So it's kind of computational problem. H plus is exists, but we cannot calculate in DFT. So we have to model it to be able to calculate it because there is no electron there. So that's why if you just put hydrogen plus and then you calculate with the Gaussians, it will be error. Okay, we will continue to the second one, the case study of helium. So we will have 4 equations. The first one is we ionize the helium with, we put 1 electron. So it becomes helium minus 1. And then the second one, we will do the first ionizations. So this is the helium and then helium plus 1 and plus 1 electron because we take 1 electron here. And then in the third, helium plus, we take 1 more electron from helium plus. So it will become helium 2 plus electrons. But we also can take both electrons at the same time. So that will be the different. So when you took the 2 electrons, there will be 2 pathways. The first pathway is both electron, you take it instantly at the same time. That will be for the equation, 4 equation, please. And for 2 and 3, there is a 2-step to take 2 electrons. So the first one you take first, and then you take the second one. So for the helium, we have 4 equations. So what we need to calculate? So we need to calculate the helium atom, and then helium minus 1. And then helium plus 1, and also helium plus 2. Can you understand? Because we need to calculate the energy of product and then energy of reactant. So you can subtract the product minus the energy of reactant. Okay, so first you need to have the equations, and then you will have plan what I need to calculate from the equations. And what we need to consider first is we use B3LYP exchange correlation. And then we use to unrestricted and or restricted. And we use 2 basis set here, 631G and 631GDP. Okay, is there any question from here? Okay, so we will go to, okay. Yes, a restricted open when your system is open cell. Or there is unpaired electrons.
So it's the same.
Yeah. Yeah. So it's restricted. But actually, unrestricted is for open cell. Restricted is for closed cell. Closed cell means all of the electrons have been paired. There is no unpaired electron. If you have just one unpaired electron, your system will be open cell. And the Gaussian will be automatically use unrestricted. If you have closed cell, the Gaussian will, as default, they will calculate restricted one. But how if you have open cell system, but you need to calculate with restricted? That will be restricted. Any question? From UTM and also from UNSUD? Okay, I will go on in the tabulations. So here's so small. So here we have, this is, I show you how we tabulate the result. So the first, if I were you, I will tabulate the total electronic energy first in heart rate. And then from previous presentations, I know that I need to calculate helium neutral and also helium +1 as cation, and then helium +2 cation and helium -1 cation. And I have to consider both unrestricted and restricted B3LYP. We put here. And I also consider two basis set here. So I already calculate, so I just put the number here. So I took the energy of helium neutral with unrestricted B3LYP is negative 2.907049. And also this number. And I check the experimental value from the IC100. Also the same with helium. So I just put the electronic energy here in heart rate. So the first one, the reactant is helium, and I take one electron, so it becomes helium +1. So how much the energy is required to take one electron? So this is total electronic energy. This is the experimental value. And this is our computational value from the FT calculations. So I have energy in here. And this is the difference energy between, this is B9, between helium +1 cation and helium neutral. So this is the ionization potential or electron affinity. electron, electron affinity, really? I take one electron. From here to here, ionization potential. So from my calculation, from my DFT calculations, the computational value, the ionization energy to take one electron from helium is 24.86 E. The value is from this one minus this one, and then I multiply to change the unit to electron volt, because this one is still H3. So I need to change it to electron volt. So that's why I multiply with 27. So now I got the, and from the CRC handbook, we take the ionization potential is 24.587. Now we can check from the CRC handbook. You can open your CRC handbook. You will find there is a chapter of ionization energy of atoms and atomic ions. There's explanations about the ionization energy. I will not explain to you or read it because it will be your task in the result and discussions. So you have to read it carefully and then explain it like that. Now, here we have, Dr. Lucia, can you see it clearly, the CRC handbook? Okay. And here we have, this is the number of atom, and then this is the element, and this is the first or singly ionization, this is the doubly ionization, and third, and so on. So for hydrogens, why it is only have one number? Yeah, because hydrogen only have one electron, so that's why we only can do the singly ionization. So this is the energy required to take one electron. In case of helium, so when we take one electron, we need 24.58 electron volt. And after that, we need more energy to take the second one. The second one will be 54.40 for one electron. So this is for the singly ionization. This is for doubly ionization. So this is energy required to take one electron. This is the energy to take the second electron after first ionization. So this is after first ionization. This is also. So this is the energy required to take the third electron after second ionization. So this is not the same with you take two electrons, but this is you take the second electron after second ionization. So if you take two electrons, you have to plus this one with this one. So the energy total, if you take two electrons, it means 24.5 plus 54. If you take two electrons. If you take one electron, it's only 24. And there's interesting here because why the second ionization always take more energy than the first one? Yeah, you have to find out. Why? You can see here, there's 24 and then the second always higher. So it's mean it's harder to take the second electron. So the first electron will be easier than the second. The second ionization will be easier than the third ionization. And the fourth ionization will be easier than the third ionization will be easier than the fourth. That's interesting here that you have to find out later. Here is the experimental result, but I don't know about your calculation. We'll back to our regulations. So here we have 24.587 from our book here. Just take this number as the experimental value. And this is our calculation. This is my calculations. And then the third task, you need to, so the first task is you have to calculate, you do the DFT calculation. And then the second one, you take the experimental value from the SCRC handbook. And the third one, you have to compare with experimental. So how many percent of the error? And from here, the error is very small, 1.14%. It's in percent. So it's very, very accurate for helium. So you can do the same thing with the 5 other, with 6 atoms. So the hydrogen atom and also 5 traces atom. Okay, and then we also can get the electron affinity. So here the ionization energy of atom and atomic ions. And also we can we're looking for the electron affinity. How to get the electron affinity from the SCC. Here's the electron affinity. So you need to read this one. So what is the definition of electron affinity? Here there is the definition. You can read and also answer the questions. And then here is the atomic number and then formula, name, electron affinity, and this is the uncertainty or the error. And then this is the method. We have to explain the method, right? And then the reference. So you have to know what is COP, what is LPT, what is LPES. You have to find out. For example, we have helium here. How much is the electron affinity? Unfortunately, it's not stable in the experiment. So we cannot take the electron affinity here. So there's no experimental result because it's not stable. So the data here can be the reason you choose the atom. Because you need to find out the accuracy. So you need to have the experimental data. So please consider to choose electron that has electronic affinities data here in experiment. So you can compare them. So for example, you choose carbon, the electron affinity of carbon is 1.26. So the error is 0.00 blah 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 electron. So there is the uncertainty is very small. And this is the method LPT. For example, you can check here LPT is laser photo detachment threshold. And you can research in internet what is laser photo detachment threshold. Okay, clear how to calculate ionization potential and also electron affinity. So we can but even though we don't have the experimental result, we can still calculate from the DFT calculation. We can subtract from the helium neutral with the helium -1 anion. So we get the number is 35.986 electron volt. Is there any question for calculating the electron affinity and also ionization potential? So the first one, you have to make the reactions and then your calculation design. You design a plan, what you will calculate. And then the third one, you calculate the both energies. And then the fourth, we will have to compare with experiment to get the POC. Is it clear? Okay. We will back to the module A3. And here, so there is two ways to calculate the ionization energy. First is from the electronic energy, and second one is from the orbital energy. If you read the Dr. Fakken books, the second book, with the Hilal as the cover boy, you will find in chapter 12.2. It's about AOM, free electron non-interaction. So we will read a bit about why we can use the quantum orbital to calculate the ionization energy. Here's the explanations. I will speak in Bahasa. Is it okay, Dr. Fazira? Because the book is Bahasa. Okay, in here, uraian bab 12.1 adalah cara Konsam membuat sebuah EOM1 elektron pengganti Thise banyak elektron. Beliau berdua menggunakan persamaan eigenvalue 3.6 dengan Hamiltonian Konsam dan orbital Konsam berturut-turut sebagai Hamiltonian dan eigenfunction. Mereka dapatkan EON, key electron, non-interaksi. So this is the equation, the quantum equations. Here is the Hamiltonian quantum orbital, quantums, and here's the orbital, and this is the energy of orbital. But the important thing here is the quantum orbital is from the non-interacting system. So that the orbital and energy of orbital is associated with that orbital has no physical meaning. So the quantum orbital is built from the non-interacting orbital because there are a lot of approximation before. Because if there is no approximation, we cannot calculate. So we build the quantum orbital with the non-interacting orbital. So the consequence is the orbital and the energy of orbital have no physical meaning. But amazingly, mashallah, empirically, the quantum equation can predict the orbital and orbital energy that is observed in experiment. You get the point here? So the quantum orbital is built from the non-interacting orbital. That means because actually the orbital is interact with each other, but because of there are a lot of approximations, so we just build from the non-interacting orbital. So that's why the energy and orbital have no physical meaning. But amazingly, it can predict the orbital energy that is observed in the experiment. So one of the theory is the Janak theorem. So in Janak theorem, we know that the change, so we'll zoom in. So this is the Janak theorem. So the change in the total energy because of the change of the number electron is equal to the orbital energy in orbital E. I repeat once again. The Jamak theorem is the change in total energy, because of the change of the number of electron in orbital E, it's equal with the energy of the orbital energy of orbital E. When we take the electron and put electron, do the number electron change? If we take one electron, is there any change in the number of electrons? Yes. Is there any change in the electronic energy? Yes. So that's why we can use from the Janak theorem, we clearly can take the orbital energy to calculate the ionization potential and also electron affinity. So here, this is how we calculate the ionization potential. So ionization potential is Q is the number of electrons. So the first one, if we have, for example, hydrogen. Helium has 2 electrons. So that's why helium will be 1 plus 1 here, minus energy of helium plus 1. So the ionization energy would be highest occupied molecular orbital, or the highest occupied atomic orbital. That will be the ionization energy. And also for the electron affinity, you can take the lowest unoccupied. So the first one is the highest, but it's occupied. And then for electron affinity, you can use the lowest unoccupied atomic orbital. There is two ways how to calculate the ionization energy. First is from the first one that I show you in this table. We extract from the total electronic energy. But for the second one, we need to tabulate the orbital energies. For example, this is the helium neutral. This is the helium neutral. And then this is the orbital. The helium has two orbitals, right? It has two, one s and s here. And this is the energy in heart rate, and this is energy in electron volt. So which one will be the highest occupied atomic orbital? It will be 1s. Because the helium is 1s2. We have two electrons, right? So you just take this one. For ionization potential. But for electron affinity, you took this one. Because this will be the lowest unoccupied atomic orbital. And you can compare with the experiment and then with the, so you will have three values here. Value from experiment, value from the extract from the electronic energy, and then the third one you can extract from the HOMO or LUMO, from the orbital energy. And you can compare which one is more accurate. There is two ways to predict in the FT, from the electronic energy and then from the orbital energy. Just make the tabulation. This is for the restricted, but for unrestricted, you'll find two kind of orbitals, right? Alpha and also beta. You have to tabulate the alpha and the beta, so you know the difference. So when you calculate restricted, you only have 1s and 2s. But when you calculate with unrestricted, you'll have 1s alpha and also 1s beta. So which one you will choose? To calculate the ionization energy. Which one is easier? Which one is easier? The restricted one. So you have to tabulate first, so you understand what is the problem here. Okay. Okay, I will give you a break for maybe 3 or 5 minutes, Dr. Lucia, to write a note or to think.
Sure, Dr. Vera. 5 minutes?
5 minutes is okay?
Okay, 5 minutes. You can complete your notes. And if you have questions, you can ask. They can ask later. Or will you continue after 5 minutes, Dr. Vera?
Yeah, they can ask. If no, I will continue.
All right. Okay. So we have 5 minutes break. We will start again at 11:20 Indonesian time or 12:20 Malaysian time?
The difference between unrestricted and also restricted. And then the second one is the ionization and reaction. Is there any question on the answers?
There is no questions currently from Unsud. How about from UTM, Dr. Fazira?
All is okay now. Just one of the students asked if whether they need to do both restricted or unrestricted for all elements. Calculation, yeah.
They do all unrestricted and calculations.
So they have
both.
both for all elements.
Yes, for 6 atoms.
Because is it okay if they just like choose maybe helium to do restricted and unrestricted, and for other element they have to choose and they can give the reason why they choose restricted or unrestricted, because they should have the idea by the calculation for the helium one. Is that okay or still need to do all?
How? Okay.
Didn't know that. Can you hear us, Dr. Vera?
Yes.
Oh, okay. Is it clear? Clear enough?
Yes, we can hear you clearly.
Okay. So is it necessary for them to do the unrestricted and restricted for all elements, or is it all possible to whatever? Is it possible to do only for one example, and when they have determined under what condition they should use restricted, unrestricted, then they can apply that to other elements? Is it possible, or should they still do everything for all elements?
Dr. Vera?
I was thinking.
If we take a look at question 4 in module A3, it says that write your plan to finish this project. Consider when to use the restricted and unrestricted spin methods in your analysis. So I think if they know already when to use, then maybe they can make their justification. But if they don't, maybe it is better for them to calculate first. So
Yes.
they can understand what are the differences between the restricted and unrestricted spin methods.
Okay.
What do you think, Dr. Vera?
Yes, actually for the open cell, they need to calculate with restricted open limits. So, but they have to find out why.
So that's why it's important to have at least helium
Yeah,
to do
yeah.
both, and then
Yeah.
after that they just give the reason why they choose either method. Fine. Okay, clear. Thank you.
Is there any question from Unsud?
There is no question from Unsud currently, Dr. Vera. Maybe we can continue with the questions from ITERA before.
The first question is, what is the difference between the restricted and unrestricted? So basically the unrestricted is the calculation technique to calculate the unrestricted is for the open shell. Open shell, if you have the system that has unpaired electron. So the Gaussian width by default will calculate if there is one or more unpaired electron, the Gaussian will by default will calculate it using unrestricted calculation technique. But if your electron, all of the electron is paired, it will be by default, the Gaussian will calculate with restricted. But we can also calculate if you have one unpaired electron or more, you want to calculate restricted, you can also do that with restricted open. So it's kind of the calculation technique. So you can calculate efficiently. That's the difference. For example, here in here, this is when you calculate with the restricted. You will only get one s orbital. But it will be different if you have unrestricted here. Because you will have one as alpha and one as beta. You have two orbitals, right? The left and the right. The alpha and the beta. That's a different. Okay, that's the first question, Dr. Lucia. And then the second one. Oh. Oh, the difference between ionization energy and the electron affinity. So he misunderstood. Here, the electron affinity and ionization potential is the ionization energy. So the energy that we need to ionize the atom. There are two kinds of ionization. You ionize and become the positive ion. And the second one, you ionize, it become the negative ion. If the product is the negative ion, the energy is called electron affinity. If the product becomes positive ions, the energy that needed, it's called ionization potential. But it doesn't mean that ionization energy is only ionization potential, no. So both of the quantity is ionization energy. Okay, maybe that's all, Dr. Lucia.
All right. Thank you very much, Dr. Vera. Okay, so guys, you have heard Dr. Vera's explanation about Module A3. And now, do your eyes wide open that Module A3 is easier than Module A1 and A2? Setelah mendengar penjelasan Dr. Vera, tentunya kalian semakin paham. Oh, benar. Ternyata modul A3 ini jauh lebih mudah daripada modul A1 dan A2. Yang di ITERA senyum-senyum, Alden langsung ketawa. Setuju, Alden?
Yeah, the widely smile.
Ya, nah modul A3 ini lebih sulit kan ya? Oleh karena itu, wajib banget kalian harus diskusi dalam kelompok. Jangan ngerjakan sendiri. Ya, kalau ngerjakan sendiri kesulitan, nanti berhenti. Tapi kalau bekerja dalam kelompok, kesulitan kalian bisa tanya ke teman. Nah, since module A3 is more difficult than module A1 and A2, that's why it is a must for you guys to discuss in the group. Don't do it alone. Don't be miserable alone. Share it with your friends in your group, okay? You have seen that in the previous modules, you guys were asked to tabulate and visualize. Tabulate the ground state energy. Visualize the atomic orbitals. But this time, the level is higher. Tabulation, the ground state energy is so yesterday. You just submit the work yesterday, right? But this time you need to use those values, the ground state energy, and also the atomic orbital energy to calculate another value. Nah, sebelumnya di modul A1 dan A2, kalian belajar untuk menabulasi sejumlah besaran hasil dari kalkulasi DFT. Contohnya, energi keadaan dasar, lalu energi orbital atomik. Nah, tapi itu so yesterday ya. Sekarang kan kita buka babak baru nih. Nah, di modul A3 ini kalian akan menggunakan nilai-nilai tersebut untuk menghitung besaran yang lain, yaitu elektron affinity dan apa satunya? Ionization potensial. Jadi apa yang diukur di eksperimen bisa kita replikasi dengan DFT sekarang. Nah, tapi persoalannya bagaimana kita memodelkannya supaya kita bisa menghitung apa yang diamati di eksperimen itu. Okay, so please once again discuss in the group, and if you don't have questions, we also still have time. You can ask. You can ask to Dr. Fazira, to Dr. Mark, to Dr. Vera, and from Unsud you can ask me also. Okay. If you have questions, you are free to ask in English or in Bahasa. Okay. Since we are done with module A3, we will go on with module A4. So module A3 is due on Saturday next week. You guys have 1 week to work on this module. And then you have to submit it by Saturday next week. Now, we will continue with module A4. We will introduce you. I believe that you all have module A4 already. So we will read the questions together. So you know what the question is, what the task is, what the task to do in module A4. Okay, so I'm going to share my screen. Okay, after we learn about ionization potential, up to module A3, what we have, the calculation that we perform is energy calculation. In module A4, it is about geometry optimization. You guys have this module already. Please start by reading the objectives and also the introduction and prerequisite. But for today, we will read together about the project description, results, and discussion. Okay. So for module A4, which is due 2 weeks from now, it's 2 weeks from now, around the end of December. The project description for module A4, the molecules of interest, there are 5 molecules of interest, which are H2, O2, N2, F2, and Cl2. So we no longer talk about atoms here, but we talk about molecules, the simplest molecules, diatomic molecules. And the method and basis sets are Hartree-Fock and B3LYP, 321G, 631G, and 631G D, P. What is the objective of this project? To find the optimized bond length. Since we discussed about molecule, it means there is bond length inside the molecule. So the goal of this project is for you to find the optimized bond length of the molecule, which we symbol it as R0. The routine that you will use is OPT, which stands for optimization, and scan. Use both routines separately. It means you use optimization first, and then in different calculations, you use scan. Okay. The initial distance, Ri, is as close closest as possible. So Ri is the initial distance between the two atoms inside the molecule. For example, Ri for atom 2 at 2 of hydrogen atom in hydrogen molecule is Ri, and you have to make their distance as close as possible. Okay. Note the routine scan. For the routine scan, the final distance or RF equals to R0 plus 5 angstrom. R0 is the value that you have obtained here. So it means, looking at this formula, it means you have to find what R0 first before you can determine what RF is, right? And the additional routine is GF input. Okay, and then what to do in results and discussions? Let's take a look. There are 3, 4, 5, 6 things to do in this module. The first one, briefly explain what SCF done. Briefly explain what this term means, the part that I block. The SCF done, E, open bracket, R-B3 LYP, close bracket, equals to negative 1.16428358776 AU after 7 cycles. Briefly explain what that is. The second question, what is the main indicator that the routine optimization has completed? You have performed the energy calculation before. This time you will perform the optimization, geometry optimizations. Now you need to show what is the main indicator that the routine that you are performed is completed. The third question, fill the following table with the number of SCF done and the job CPU time in second and perform comparison analysis. So you have to do both, I think, for this. So this is the table. Complete this table with the number of SCF done and the job CPU time in seconds. Next, briefly explain the similarity and the difference between two routines, optimization and scan. What are their differences? Next, fill the following table. Fill the following table with the worst accurate method and the best one in predicting the value of R0, followed by the error percentage with respect to experimental value. It marked as ERR here in the table. Perform your comparison analysis. So even though it is not mentioned here, it is not, there is no column for experimental results here, but the question require you to compare your calculation results with the experimental value. And the last question is conclusion. There are 2 conclusions that you have to make. First, identify which ones are the physical problem and which ones are the computational problem from all the results and discussions. It means from question number 1 up to 5. And B, give your opinion of the use of the FT calculation using 2 different routines for geometry optimization. The 2 different routines are routine scan and optimization and scan. Hint, there is a hint here. For routine scan, you can refer to reference 2 at chapter 6.3. Reference 2 is the textbook written by Dr. Febrian. The title is Fisika Kuantum, Fungsi Gelombang, Energi Potensial, dan Operator. I think some of the students have this book already. So go open this book, go to chapter 6.3 and find out about what routine scan is about. Okay, so that's about module A4. Maybe next we give them time to take a look at module A4. And if you have questions, you can ask. And also about module A3 before, if you still have questions.
There's no question from Itera.
All right, thank you, Dr. Vera. In Unsud also, there is still no questions. How about from UTM, Dr. Fazira and Dr. Mark?
For now, I think there's no question. Ada soalan? Any question? Tak ada? Oh, tak tahu nak tanya apa?
Semua tahu.
For now, there's no question
Yet.
yet.
Okay. We still have another 17 minutes. Do we give them time to discuss in group to plan their work in module A3 and A4?
Yes, sure.
Maybe around 15 minutes. I will make breakout room. You guys can go to breakout room to discuss for around 15 minutes.
Okay, sure.
Okay, I have made 20 rooms. You can enter the room according to your group.
First, I discuss. Check it out.
Take picture. Don't forget to take picture also because you will need the picture for your module.
Yeah, okay.
I'm afraid that you have to continue with the next class there.
Sure.
Right.
Okay. So I will close the breakout room so they all can come back to the main session.
Ako tadi phone ko ni, kami ako sakit hati.
Karen, you punya manager.
Dah aku tak angkat masalahnya. Bodoh betul lah, aku tak boleh ke.
Alright, guys. So we are in the end of our class today. Before we say goodbye, let's take picture first for the second time. Please open your camera. Nabila,
Yes, Dr. Lucia.
thank you.
How many slides is this?
Please open your camera, guys. Let's start, Nabila.
Now we're going to take a picture. Only one slide here. Please. 1, 2, 3. Wait a second. Let me check it first. Okay, once more. 1, 2, 3. Okay. Let me check this first again. Got it, Dr. Lucia.
Thank you, Nabila. Okay, let us close today's class with a closing prayer. Dr. Vera, can you please help?
Subhanakallahumma wa bihamdika asyhadu an la ilaha illa anta astaghfiruka wa atubu ilaik. Rabbana taqabbal minna innaka antas samiul alim wa tub alaina innaka antat tawwabur rahim.
Thank you very much, Dr. Vera. Thank you, Dr. Fazira and Dr. Mark. Guys,
Thank you.
see you next time. See you next week.
See you.